Welcome back, everybody. Today we're going to be looking at centripetal acceleration and try to fully understand what it is, because if you understand this concept pretty well, you should be able to solve problems more effectively and more efficiently, because you won't have this conception of acceleration incorrect in your mind. And what's important about centripetal acceleration, it explores the ideas of acceleration for objects that move in arbitrary paths, such as this. It's not moving along a straight path, it's going around something that looks like this. And hopefully by understanding this will get rid of those misconceptions about acceleration. So the first thing we're going to look at is Newton's first law. And what that says is an object will stay in motion or stay at rest unless a force is going to be acting upon it. So what I'm saying is that, let's say we have this particle and its trajectory is along this straight line. If it's moving along this straight line, it will continue to move along that straight line forever, because there's no force acting upon it. Now, if we add maybe some frictional forces, such as this one right here, the object will slow down and possibly move backward. But we're assuming that there's no forces acting upon it. So this is where the idea of centripetal acceleration comes in, and this is also where misconceptions come in. So if we look at an object, so let's say we looked at this object right here, and we drew the trajectory into a circle. A perfect circle. I know this is not drawn perfectly, but let's say this is a perfect circle and it has some radius r. And we also say that this object is moving in at a constant velocity, so it has no acceleration, at least in the tangential direction, but it will have some sort of acceleration, and I'll get to that. So if you look back up here, it says that an object will stay in motion unless a force is acting upon it, and it will go along a straight trajectory. If it did move in this direction, that must mean there must be a force pointing that way to cause this object to move or change direction, because naturally that it's just a fundamental thing in nature that objects will tend to move in one direction, and if they do change direction arbitrarily, there must be a force acting upon it. And if we go back to Newton's second law, F equals ma, if there's a change in direction and there's a force acting on it, there must be some sort of acceleration acting upon it. So although in this picture we have a particle moving in a circle with constant velocity, meaning there's no acceleration going in this direction, but it does move along a circular path, there must be some sort of acceleration to cause this object to move in a circular path. And that's the idea of centripetal acceleration. So although this object is moving at a constant velocity tangentially to this path, then what we can say is that there must be an acceleration or a force pointing that way to cause this object to change direction at any given moment of time. So therefore, this right here is called centripetal acceleration. So the key point here is that although an object may be moving at constant velocity, if its path or the vector of velocity is changing over time, it must mean that there is acceleration. So let me explain that. So we could look actually at another point later for this particle, and we could say that the velocity vector is directly to the right, and it's the same constant magnitude, because again we said this velocity vector is constant in terms of its magnitude. It's going at a constant velocity. But however, if you look at, let's say this is time equals 0 and this is going to be time t1. So if we look at t and t1, the magnitude of the velocities at t equals 0 is equal to the magnitude of the velocity at t equals t1. But if we look at the vectors themselves, they don't actually, they're not congruent, because one is pointing upward and this one's pointing to the right. So what we can say is that velocity vector of t equals 0 does not equal the velocity vector at t equals t1. And since this is true, that means there must be some sort of acceleration vector that is changing this velocity. And that's this centripetal acceleration. So the key point, again, the key point is to recognize if there is just a directional change in the velocity vector, there must be some sort of acceleration. And it's usually just centripetal acceleration. So actually, this is just a special case, this circle right here, because this is just an ideal circle. This is a very special case. Now let's generalize this a little bit more, and actually this is where this idea gets applied to dynamics. So let's just take an arbitrary path for this particle. We could say that this is the particle and it's going along the path in that direction. So what we can say, this is very crucial to understand, is that any point along this curve, let's take that point example, we can actually define that point relative to some circle. So if we look at this point and we make a circle, let's say it's tangent to it. So if we draw a circle right there, it's not the best circle, but you guys get the idea. It only touches at that one point. What we can say is that for that given point, it has one type of centripetal acceleration that is defined by this circle. So we could say that it is the centripetal acceleration at this given point. Now, if you look at some time later, we obviously see that this circle changes. So let's say this point right here. If we draw a circle that is tangent, and what's special about these circles is that the radius changes as a particle moves along the path. And if you look at this point right here, the centripetal acceleration may be a little bit smaller. So what you can do is actually define this whole path as just circles being tangent to it. And one thing to notice is that the circles always point in the concave direction, if that makes sense. So it's always pointing in the concavity of the path. So you will never see the circles being drawn in this direction because it's not pointing in the concave direction, so to speak. So we could now use this idea to create formulas that are dependent on these radius of curvatures. So that's what these circles are called. This radius of curvature would be that radius defined by this arbitrary circle, and this radius will be defined by this circle at this given moment of time when the particle reaches that point. So I found this little program to demonstrate what I was talking about earlier, and this is made by interactivemath.com. I'll leave a link in the description so you guys can check this out. But what I'm saying is that at any given point, you could define a circle with some radius of curvature. And as you can see, this at point P, it's defined by this pink circle. But what we can do is actually change this circle as it moves, as an object moves along this path. And right here, it switches concavity because the path switches concavity. So the circle switches its orientation as it moves along the path. And we can use this idea to find centripetal acceleration, because later on we'll see that centripetal acceleration is actually dependent on the radius of curvature. And you can see that this changes over time as the particle moves along a path. So this is just a good demonstration of how this thing works. Again, I'll leave a link in the description or in the comment section so you guys could check this out and play around with it. So I just wanted to write out the key idea. If the path of a particle changes over time, then the particle is accelerating regardless of constant velocity. So if we look back at this diagram, if this particle is moving at constant velocity, but it changes over time, if the path changes over time, it does have acceleration. And in that sense, it's a centripetal acceleration, which is dependent on the radius of curvature of the path at any given point. Now, I'm not saying that if the velocity does change over time, so if it moves faster at this point than this point, then it does have two components of acceleration. Acceleration that is tangent to the path, as well as acceleration that is perpendicular to the path, or the idea of centripetal acceleration. But it's just key to understand that if the path changes over time, there is acceleration regardless of constant velocity. That is a very crucial thing to understand, and many people forget this idea or have this misconception, and definitely just forget about the idea of centripetal acceleration. So please remember this. We'll be using this idea later on.